everyone, my name is Alejandra Baena and I am a rising senior at the University of Pennsylvania. I currently work at the Penn Digital Neuropathology Lab under the supervision of Dr. David Irwin. Thank you so much for joining me today as we learn about my research project, Improving Neuropathological Analysis in Immunohistochemistry through Starburst artifact detection. So why is this research project important? Our lab is currently developing what we call SANA, or Semi-Automated Neuropathological Analysis, which is a toolkit that allows us to segment neurons, plaques, tangles, and other objects that measure the degree of pathology and degree of neurodegeneration. However, within our tissue, we often find these artificial staining marks, known as artifacts, that afflict the accuracy of the models we're creating and cause inaccuracies in the measurements of pathology or degeneration. Therefore, the aim of this project is to develop methods which detect and remove staining artifacts from our post-mortem human brain tissue images. As you can see here, our dataset included ROIs that have artifacts as well as representative ones that do not have artifacts. And for our image processing, our first steps were the pre-processing ones, where we separated the DAB stain and used various filters, including the anisotropic diffusion and morphological opening filter, to be able to better detect the artifact. And we also perform a stain thresholding to remove insignificant background staining. Later, we have our object detection steps, where we use a clustering algorithm known as dbScan, which extracts core points within the artifact image, and we then are able to convert this into a polygon and extract the object using a script that converts it into a JSON file. After that, we have a template matching system where we are able to yield a confidence value, which is the probability that a segmentation is a Starburst artifact. And we developed this template using a 2D Gaussian probability density function kernel. Later, for our post-processing, we're able to reject detections based on minimum surface area as well as the confidence threshold value that I mentioned before. And we're able to create a scoring analysis that outputs both false negative detections, false positive detections, and true positive detections. Once we have our scoring system in place, we are able to measure the score, which we call IOU, intersection over union, between the manual or reference annotation that we created and the annotation that is outputted by our system. And we're able to score this using what we call our precision recall curves, and we're also able to output average precision values, which, as I mentioned before, we use this value known as IOU. And in both the graph and the table, we're able to see that we achieve higher precision and recall values, as well as high average precision values whenever we're using a low IOU threshold. And this is so far what our system is able to work best at low IOU values. Therefore, our conclusion is that our system is working really well at low IOU values. However, for the SANA pipelines, we will require a better performance at higher IOUs before we can implement it. Therefore, this is something that we need to work on. And in order to be able to improve this measurement, we have a few future directions, as well as be able to implement it into our pipeline. We will run it on a larger data set, and later we will optimize the image processing parameters and techniques, so the different values that we use for the parameters that we implemented within our detection system. Later, we will expand the artifacts to be able to detect tissue tears, blood vessels, and other important artifacts, not just Starburst artifacts. Thank you so much for staying throughout my whole presentation. I hope you were able to learn some cool things about digital neuropathology, and feel free to ask me any questions at my email, and I hope you have a wonderful rest of your day.